Remember that carbon cycle is really a very vast topic, and we are just going through a primer so that you are generally aware of the landscape of carbon cycle, and you can follow up on the details as you wish. So how do we discuss the future of carbon cycle? So essentially it's important to just look at what are the sources and sinks are and what they would do in the future, which is essentially, let's say, out to 2100, which is the time horizon we are typically focusing on, even though most people are now backing down and saying we need to plan first for 2030 and 2050, and very few people pay attention to 2100, and there are way too many uncertainties with the models, with the scenarios we assume to project to 2100 and so on and so forth. This is the typical kind of figure you will see where there is a partitioning of the carbon cycle from 1850 onwards to here about, let's say, 2015 or so. This is extended every year. The positive numbers here in terms of CO2 flux gigaton carbon per year are sources into the atmosphere. So you have fossil fuel and industry emissions being the biggest sources, which have increased over time steadily, and maybe accelerating, definitely accelerating over here. Land use are things like deforestation, conversion to agriculture, urbanization, forest degradation, and so on and so forth, draining of wetlands, loss of salt marshes, etc., which add a bit of CO2 flux to the atmosphere as well. And then you have the sinks, where ocean is doing quite a bit of heavy lifting, taking up carbon dioxide. It also takes almost 93% of the excess energy that's created by increasing greenhouse gases. So ocean is really modulating global warming, and we are lucky. Of course, if it belches it all out one day, it's going to be big trouble, but nonetheless, because it's deep and because it covers so much of the surface, almost 70% of the surface area of the planet, it continues to take up heat and carbon, so that is shown here. The question really is, going into the future, whether the ocean continues to take up carbon like this, or the warming and the stratification of the ocean. If you warm the surface layer, the gradient to the cold water below is going to get stronger, so mixing is going to be harder, which is what we call stratification. And whether that will reduce the ability of the ocean to continue to take up carbon, that's something about the future we have to worry about. Land has this up and down here, and there is something called missing sinks. So often the two don't match up, so there are gaps, residuals you can say. People hesitate to call them missing sinks, but essentially they are uncertainties in closing the gap. We will see that this is a problem into the future as well. The rest of it is obviously accumulating in the atmosphere, which is much more easily measured, and the residence time of carbon dioxide in the atmosphere is centuries to multiple centuries, which is why we have things like committed warming, where we have been accumulating carbon dioxide, which will continue to warm the system for a while as the rest of the sinks continue to take it up and reach an equilibrium over time. Sea level will rise because of the warming of the ocean, melting of the glaciers, etc., etc. We are obviously creating all sorts of sources of carbon dioxide, including methane, which has a very relatively short residence time of about a decade to 12 years and is easily oxidizable, so, and we are using it as a fuel as well, so that gets converted into CO2 as well. There are emissions and sources and sinks that we have to worry about. Models want to take care of all of these things and then try to estimate, as anthropogenic emissions continue to increase. Despite the 25 years of negotiations, we haven't managed to reduce the emissions yet. Then what actually happens? So we are looking at enhanced uptake by the ocean, by vegetation, land and so on and removal. So we're looking at negative feedbacks in the system and the warming that is going to create drier conditions. Even though temperature warms, atmosphere warms, it holds more moisture. This moisture is not uniformly distributed because of the dynamics and the circulation, the details of which you can find in my other courses on my YouTube channel. So you are creating many situations where wildfires now seem to have increased or at least become more widespread and longer lasting. So that's going to release a lot of the carbon that's been assimilated by photosynthesis to be released at a very fast rate, and that's going to have an increase in the carbon dioxide, so you can have positive feedback. So the future is very uncertain, and this is very obvious when you look at the annual land fluxes in petagrams carbon per year. As we said before, petagrams is 10 to the 15 grams, which is a gigaton, 10 to the 9 ton, or a billion ton. And here we are talking about carbon, not carbon dioxide. And you remember there is a 3.7 multiplication factor going from carbon to carbon dioxide. So you can see that the models try to reproduce the historic variability of the land fluxes, try to compare to observations, or often constrain them from observations and so on. But when you go into the future, you can see that there are, I think, 11 models here, and they all have different ways of representing the land biosphere. There are also differences in the atmospheric model, ocean component. They may not have land glaciers, for example, sea ice, so on and so forth. Nonetheless, carbon cycle remains a large uncertainty. So you can see that some are saying increasing emissions from land, and some are saying steeply decreasing emissions from land. So the future of carbon cycle remains quite uncertain, and every time you look at projections for the future, you have to remember that these future projections have scenarios on which these projections are made. How we protect land, how we increase agricultural land, how we urbanize, how we protect forests, how we use transportation, and so on and so forth. Nonetheless, you can see that the future of carbon cycle is quite uncertain. So that also adds to the mood of the carbon cycle. So this is a relatively short introduction to the different time scales at which the carbon cycle behaves differently. On geologic time scales, longer than glacial, interglacial, let's say, carbon dioxide weathering is a negative feedback. Warmer temperatures increase weathering, colder temperatures reduce weathering. And glacial, interglacial, the CO2 and methane follow the temperature, and they are also positive feedbacks in both glaciation and deglaciation. And now we have to worry about the future, and we are not completely sure whether it will be a net negative feedback or a net positive feedback. Okay.